Hi, this is Kyle, and this is my presentation on Project 2, the bipartite network analysis on a dataset of our choosing. I chose my set from the Connect site, and I chose a membership network of GitHub users and projects. The dataset was collected in 2009 during a contest, and it contains users and projects. Each edge indicates that the user is a member of the GitHub project. Let's take a look at the size of this network. It has 120,000 nodes and more than 400,000 edges and 3 component subgraphs. Now, from playing around with this, we're going to need to drastically reduce the size of this network before we do our projections. This is because if we don't, it'll create unipartite graphs that are tens of millions of edges. And there's about roughly a third to 2/3 breakdown between the user nodes and the project nodes in our network. When we take a look at the subgraphs, we see that 2 of them only have 1 node each, so we'll drop those. And because our graph isn't weighted, we can't directly apply the island method demonstrated in the book. Instead, we're going to use the example from chapter 3, and we're going to trim nodes based upon the number of degrees. And we're going to do this based upon how these degrees are distributed among the project nodes here and the user nodes here. In order to get this graph down to a reasonable size for our notebook analysis, we're going to select only the users that have between 3 and 20 degrees and the project nodes that have exactly 49 collaborators. The resulting network has much fewer nodes and edges, but it still has over 10,000 component subgraphs. So we're going to trim those and keep only the largest subgraph, which has about 5,000 nodes and edges. And we're going to project these into unipartite graphs here. And the unipartite user graph has 5,000 nodes and about 9,500 edges. The plot shows a network that has a moderately dense core with some peripheral nodes. Let's take a look at user centrality. We're going to use this function here to go over the 4 different centralities on this graph. First, degree centrality. It's calculated by counting the number of edges for each node and dividing by 1 less than the number of nodes. And when we look at degree centrality for this user graph, we see that the mean is small and the range is narrow. It's concentrated around 0, as we see in this histogram. And here are some of the top GitHub users by degree centrality. And let's compare degree centrality to eigenvector centrality. Eigenvector centrality is like a weighted version of degree centrality. First, the distribution is a little different. It's very bifurcated, where nearly all of the users have an eigenvector centrality near 0, except for a tiny little clump that have a centrality value of over 0.2. And when we look at the top 20 of these nodes, we can see that this clump it has about 16 nodes in it right here. And when we compare the top 10 degree centrality nodes to the top 10 eigenvector centrality nodes, we see that there's only 3 in common, which reflects the weighted aspect of eigenvector centrality. Now let's take a look at betweenness centrality. Betweenness is the measure of the degree to which nodes serve as bridges or bottlenecks between the network, parts of the network. And we see that this is, again, relatively small. And we will want to see if there's a high clustering coefficient that could be related to this. Finally, let's look at closeness centrality. Closeness centrality is the node's average shortest path to all other nodes scaled by the maximum distance. And this is actually the highest centrality metric of all the other centralities. It's at has a mean of 0.065. And taking a look at some of the other measures, this has a relatively decent amount of decently high clustering coefficient at 0.57. This means that this represents the proportion of mutual friends that are also connected. So for the typical GitHub user in our projected network, more than half of the mutual friends are connected. Now let's look at the clicks in our user graph. A click is a maximal complete subgraph, which means that every node is connected to every other node. And we have about over 2,800 clicks, and most of them are most of the click sizes are within single digits, and the biggest one has 17 users. Now let's take a look at the unipartite projection of the project graph. This project graph actually has more nodes than edges, which means that there are more projects than connections between projects. And it also has 13 component subgraphs, which means that for these 188 projects, the users among them can't connect all the other, these projects can't be connected by their common users. And this is what the graph of the 13 subgraphs look like. Now, let's take a closer look at the two largest subgraphs here. We're going to call these graph A and graph B. They look from these two plots, we can see that these graphs look fundamentally different than the user subgraph. In the user graph. In the user graph, there were many mutual ties between nodes, but in the project graphs, we see that there are a handful of project nodes that connect other projects together. Graph A has 60 nodes with some prominent bottlenecks and bridges, and graph B has 29 nodes. And it looks like a broadcast network with a single node connecting all the other nodes. We're going to see if our network metrics confirm what these plots look like. So first, for the plot of graph A, we would expect a few nodes to have high betweenness centrality. I'll correct that. In the table below, we see that only 5 projects have any betweenness at all. And from the plot of graph B, we'd expect only 1 node to have any betweenness, and project ACL plugin actually has a perfect betweenness with the score of 1. And given that this is a broadcast network, the ACL plugin node is also the only project that has more than 1 degree. It has a degree centrality score of 1. As we suspected, unlike the user graph, neither of these project graphs have any clustering. None of the mutual friends are connected. And since we didn't have any mutual friend ties, the largest click in these graphs is only 2. And that's my presentation for Project 2. Thank you.